So the story starts, you're trapped in a tower, but you have no recollection of how you got there or what your previous life was. Basically, you have amnesia, and then all of a sudden the wall breaks and you're set free, but there's a voice in your head that's telling you where to go and what to do. And it's a tower puzzle game. So you start at the top and you gotta work your way down to the bottom. And you're basically just trying to escape. The game develops from just straight up mazes in the dark to block puzzles, then block puzzles with water, and then ice. The goal of the game is just to escape, and at the end you encounter a guard, and if you collected enough coins, you can bribe your way out of the tower, and if you don't, then he'll bring you back right up to the start.
Okay, so looking at the code for the game now, I'll start in the main CPP file, because this is where all of the callback functions for OpenGL occur. We have our display function, which is going to draw the frame buffer object. The callback function, the callback function for the keyboard up and down. The special function is one that I added. It's for all of the arrow keys on the keyboard, which is really useful. Instead of using it, though, I think we ended up using virtual key codes from all of the objects, the keyboard objects on the computer. We have joystick compatibility, 5. I think this value is actually it's the delay in milliseconds that you're expected to receive from the controller, so it's just compensating for that. These other functions are not as important, aside from the mouse function and the passive motion for the mouse, which gets the position of the mouse constantly. So we created a window with the resolution of 1600 by 900, which is the native resolution of our laptops provided by the schools. Our game is different from other games because we use shaders. So right at the beginning, right after the game is created, I set the shaders before even initializing the game object because it's pretty important. Nothing should be drawn without these shaders. So the first shader that I load in is a vertex shader, which is written in GLSL, but it doesn't actually change the vertices at all. All it does is takes the coordinates of the texture, the UVs, and places them in the proper spots. And this fragment shader, what it does is it takes the light's position in screen coordinates and it takes some rotation matrices. And what I've done here is define some colors as uniforms up here, deserialized my normals so that they're normalized from the colors, and then I set the depth buffer. So this is what allows objects to be drawn in the correct order. Yeah, so the direction of our light is just calculated using some basic vector calculations. We subtract one vector from another, and it gives us a direction. So the way we do the lighting is we take the diffuse model, which is just the dot product of the normal and the direction of the light, and we multiply that by the diffuse color that we want. And because our game is meant to be dark and gloomy, we just we took a 70% of the color, and then we lowered the blue component by half, so that the prominent colors are red and green, so the game is yellowy. This is to make the game look like a lantern instead of any other sort of light. So inside the game.cpp function is where we have all of these functions that we define in the callback functions in the main CPP draw the sprites, we iterate through a list of sprites to draw, and we do the same for objects. So our objects are actually, I've got an objects class in our game header. This object class is the base class for all of the other classes that every object drawn on the screen is created from. So it's called game object. It's got getters and setters for x coordinates and y coordinates and z coordinates. What it does here is it just takes these and multiplies them all by 32 because it's in a grid space. So they're all just 32 times however far apart they should be. If you write a block at 0, 1 and a block at 0, 2, they're only going to be 32 pixels apart then. This gets translated into isometric space by rotating it by 45 degrees and then scaling it vertically, taking the y component and multiplying it by 0.44, which is the sine of 4 over 9 in degrees, because that's the ratio of our isometric game. It's actually dimetric, not isometric, because the angles aren't all the same. A virtual void, it's a stub function for the update, but it probably could have been purely virtual, seeing as all of them need an update function. All of these objects need all of these variables that we've declared, and so that's why they're all inside this base class. Now I can go look at some of the classes that inherit from this. You'll find most of them inside of the puzzle mechanics header. So the first one is the wall object. The wall object inherits from this game object, and you would think that there's not too much happening inside the update function for a wall, but there's actually quite a lot because the cameras don't move inside our orthographic space. They actually need to move in relation to the player, so the player has a start x and a start y coordinate. You take the difference of those and compensate for how far it should be moved in isometric space inside of the drawing of the sprite, because sprites are all drawn in isometric space. We're working in 3 different spaces here, although spaces, they're all hypothetical. They're not really any different. We've got world space, which is if our game was 3D, but it's actually 2D trying to be 3D. So the best way to picture this is that we don't actually have a Z value when we're in isometric or in grid space. But once you're in the 3D space, I'm not sure if you can see the mouse cursor, but the Z value is following this axis, the X is following this axis, and the Y is following this axis. Whereas in the other two, Y is this axis. It's like normal Cartesian grid, where Z is coming out of the screen. And that's not correct for the normals that we have in our game. So, other objects. So the player is another object that inherits from the game object, but it's much more different than any of the other objects, seen as players got all of the interactions and movement. So there's a lot of other functions in here that are required to make the game work. We have check movement input, so this will take in the W, A, S, or D keyboard buttons, or up, down, left, and right, and it will move the player based on which of those are pressed. And I'll show you what that function looks like and how I constructed that using the class. It's part of the player's namespace. It checks if you're snapped to a grid, and then it checks to see if these two keys are pressed, W and A. And this is an example. What it does is it returns after that if it's successful, because if it doesn't return and then these two are successful, then or if this is not successful, it could still it messes up. These are all listed in the correct priorities that they should. WNA is up and to the left, so that should be trumping the A and the S, which is down and to the left, which is something we learned in our digital game design class. The player's update function, we check here to see if he's pressed return or not, because return is the main interaction button, and you can see that we don't have a lot of code here because the class structures saved on line counts, and there's not much more to go over in terms of class structures, but if you're interested in the shaders, I can talk about those more some other time. I think I've gone for about 10 minutes, so I'm going to stop recording now.